There we go.
Thank you. We can hear you now.
All right, so let's restart. Good morning all to the day 3 of our workshop. This session is dedicated to improvements and advancements with the various UFS modeling components. And we'll be hearing about those, ranging from physics and dynamics advancements with FE3, sea ice, oceans, waves, as well as aerosols. And these advancements and developments for these modeling components are very important because they all then lend towards improvements in our operational, soon-to-be operational systems using all these components as part of the UFS framework and lead to more accuracy and better forecast from both GEFS and SFS. So I'd like to invite Dr. Fanglin Yang to get us started. Thanks.
Good morning, everyone. So I gave a 50 minutes will be brief overview of the development of some of the Dycore updates and also the physics for UFS applications. But at the end, I speak about the recent updates related to the seasonal forecast system. First, I'd like to thank my all the contributions made by the EMC developer and also community developers. In particular, I'd like to thank Lisa Benson from PSAR and Lydia Benedette from GSAR for their contribution and leading the community physics development, and also some of the EMC scientists who provided the slides for me and for this presentation. The outline for my talk, first about the unified forecast system application and the physics options, and the second part is about some of the major changes upcoming for the SFS development. This slide shows the current operational suites and the NCEP. You can see we have many operational models running and different Dycore, different physics. Party has seen this slide many times. As you all know, currently NOAA is collaborating with the US Weather and Climate Science Community to develop the next generation fully coupled Earth system model for both research and operational applications and across different spatial and temporal scales. Let's see if I can do this. This is schematic showing all the components currently for the UFS applications. We have the semi-permeator FE3 Dycore, CCPP, a common computer physics package, 6 ocean, low MP non-surface model, WAVEWATCH 3 wave, C6 CIS model, Go-Kart Aerosol, and also the CMAC regional quality model. And in terms of applications, for regional, we have the rapid refish forecast system, RFS, and still under development. We have the inline CMAC, the first version, went into operation last year, and we have, of course, the HAFs already. The first version was implemented last year, and this year we have the second version was also in operation. On the global side, we have the GIFS, the Global Ensemble Forecast System, the GFS Mid-Range Forecast System. We are currently developing the SFS, the Seasonal Forecast System, and also the WAM, the whole atmosphere model for space weather application. Speaking to the physics development for UFS applications, there are two major goals. One is to develop and improve physics parameterizations for UFS applications to reduce model systematic biases and improve forecasts of extreme weather and climate events and maximize model prediction scales. The second goal is to unify physics parameterizations for all applications across different spatial and temporal scale. And this is to speed up the transition for research to operation and also reduce the operational maintenance. This table shows the current physics options used by different UFS applications. And so on second column, you can see these are all global models. And in a sense, we have all unified all the physics for global applications, ranging from like the 100 kilometer resolution down to GFS version 17 will be 9 kilometer resolution. The ACM version 7 was started from the GFS version 16 phase package. You can see basically this is the version 16 phase package. For ACM version 8, we are planning to move to this suite of physics, so to unify as well. And HAFS, because it has a demand for diversity, we have HAFS version A and B. So for microphysics, both Thompson and GFDR microphysics will be still used. And we are moving towards to NOAA MP as well for next HAFS implementation, HAFS version 3, currently organized. As you all know, RFS started from the HER physics package. You can see that's why the RFS has many different physics options than other applications. And given the current uncertain status of the RFS, we'll see what the physics package will be used in the future development. So how the physics updates be made to all the applications? This illustration and put together by Lisa, of course, with the contributions for all the physics developers. We started from GFS version 16 physics package, like so-called P6, and granted and different new options, like the NOAA MP and also parameterized closure, and many other updates, like gravity drag, and also convection schemes, and so this the BU. We started early running the lower resolution or targeted for the GIFs implementation. So it was run at the 25 kilometer resolution, or called the CS384. And later we started to run the high resolution target for the GFS implementation. The target for GFS implementation will be 9 kilometer or say 1152. Usually for individual developers, they test one change controlled experiment, and then we put them together for prototypes and running prototypes for extensive evaluation and testing and evaluation. This is a very high-level summary about the major physics changes we made starting from GFS version 16 up to now. Many of the changes also have been included in the HAFS implementation version 1 and version 2. Major changes include the microphysics. We switched from GFDR microphysics to the Thompson double movement microphysics. Non-surface model from NOAA to NOAA MP. With many updates to the gravity drag, also new options be included. Also new parameterization for the convective localization and the new prognostic so-called sigma option for scale adaptive cumulus convection. And the new stochastic physics in ocean land surface and atmosphere. Also implement the new positive definite tracer activation scheme in both the convection and the PBR scheme. And also new capability for coupling between aerosol and physics, and the new land ocean lake masks, new ice climate energy, and the surface composites over Franklin grid. The Franklin grid was introduced when we started the UFS development. We also made many improvements to the convection scheme and PBR scheme, gravity drag, and also the coupling between land and the surface layer scheme. So at this point, I talk about the recent development for the specifically for the signal forecast system application. Once we started to test the hydrostatic against the non-hydrostatic option. Up to now, all the UFS applications have been run using the non-hydrostatic option. But as you know, for signal forecast, because computing cost have to run at a closer resolution than many other applications, the target is 50 kilometer resolution. Naturally, we should consider hydrostatic instead of non-hydrostatic. You can say there's a benefit. It will save about 40% of computational cost. or this including the change of the cycle, and also we can use a longer time physics time step. A few things we encountered first by extending this option is the total energy issue. The total energy was not conserved, and so we have to make some changes. The one thing we found is very extensive potential temperature calculation. After this fix, get the energy conserved quite well, and also we refer to what is the GFTR, the calamity model, and the M4 model, what they have been using for hydrostatic option. And so we have to make some changes for the many of the dynamic core options and to run the hydrostatic options. There's just listed a few, like also some of the automation schemes and remapping scheme, and also the dunking. This all have been built into our workflow. When you run the hydrostatic option, you should get these options. This is the illustration of the difference between the hydrostatic and non-hydrostatic, the impact on the median and subseasonal forecast scale, and also the NINO 3.4 scale. This is one, on the left-hand side is the actors only running up to 35 days for 61 cases. You can see overall the hydrostatic and non-hydrostatic for 500 millibar alarmic correlation, there's not much difference. All with uncertainty, and also even the first 2 weeks or so, the scale is slightly better than the non-hydrostatic. For NINO 3.4, there's a couple run, but without a wave and aerosol. This orange line is from the hydrostatic forecast. You can see it actually shows better forecast scale than the non-hydrostatic on the 3.4 on alarmic correlation. Another thing we noticed is the ozone hole in the southern polar stratosphere region, and the model didn't capture this observed ozone hole. And Daniel and Kate have been working on this. So we came up with a parameterization, and new parameterization that this one can shoot capture the ozone hole. And we are still testing this for all applications. Hopefully, we'll include it in SFS at the start, and then in all other UFS applications. This is. Another thing we have been working on, this actually has been proven very difficult to improve, is the SSD. And first, when we run the GFS version 17 phase package at a low resolution, we found the model is not code BIOS. With some adjustment to the coupling between convective cloud water and radiation, and then the model comes to ohm. It seems this feature is robust, and it doesn't change with hydrostatic and non-hydrostatic, and also both showed in the 100 kilometer and 50 kilometer resolution model, and also in different two versions of ocean model. We're still working on this, try to find the cost and improve this SSD forecast. This is my second to last slide, and a few things about the NAND process for SFS application. We are testing the 10-layer, consider the importance of NAND memory. And right now, all the UFS applications use the 4-layer NOAA MP model. We are testing the 10-layer NOAA MP model. Also for the vegetation, currently is a time-related area, deep area index. We are planning to move to first calamity tonnage has net distribution, and then later on a real-time area application derived from various satellite observation. We'll improve the slow physics, including the conductivity, slow fraction, and slow temperature utilization, and this work collaborating with the community. We are also considering whether or not to include the zero routing. It's important for the signal forecast application. Feature difference including the carbon cycle and photosynthesis. Clarity gave a presentation yesterday about the nano visualization. I skipped it here. So that's all I have. Thank you.
can do one quick question if we have. All right, thank you, Fanglin. Oh, I'm sorry.
Yeah.
I'm just curious, in North America, I can highlight the lakes, very important for setting up regional climate. Where you plan to lay?
And for regional application, the question is about the lake in the northern high latitude. In our regional application, RFS already has a lake model included. In a global model, we don't have a lake representation, but we have a plan to in the future to include a lake option. We have tried the flake lakes model, but it has not been successful. We'll revisit this.
Thank you, Fanglin.
Next, we'll be talking about the NOAA MP model. And this is from Ronnie, and I don't want to butcher your last name, so please.
I probably done it enough.
Okay. Okay.
Good morning. I am Ronnie Abolafia-Rosenzweig, not the easiest last name in the morning. So in this presentation, I'll be discussing our recent enhancements for NOAA MP focused on snowpack modeling and towards the ultimate goal of improving S2S prediction of precipitation and drought. I'd like to acknowledge the contributions from the team lead, Senlin He, as well as Sushan Hin, Fei Chen, and Mike Barlage, as well as the funding from the NOAA WPO that made this work possible. So the NOAA MP is a key land component in many offline and online modeling systems. This includes the NOAA UFS, as well as the National Water Model, NASA LIS, and others. And in the recent decade, NOAA MP has had a growing community almost exponentially. In the recent international workshop we held previously this year, there was 187 participants from 18 countries across the world, and all focused on developing enhancements and using NOAA MP in unique ways. And there's a hypothesis that the land is important for subseasonal and seasonal prediction, and with this figure well known from Paul Dermeyer. And specifically, the relatively slow varying aspects of land are considered very important for the subseasonal and seasonal timescales, with a focus on soil moisture and snowpack. And this study will focus on the snowpack developments for NOAA MP. So we're all aware of the snow albedo feedback in the climate system, but this also means our climate models have important uncertainty feedbacks related to snow. So uncertain snow can propagate and enhance various uncertainties in coupled modeling systems. So for instance, if the land model overestimates either snow depth or snow water equivalent, a land model that uses a snow depletion curve to estimate the snow cover area will then tend to overestimate the snow cover fraction or the snow coverage across a region. This leads to an overestimation of the albedo, and then an underestimation of the absorbed energy by the land surface, resulting in uncertainties between the heat fluxes between the snow and the atmosphere. And in this example, this would favor a cold bias in the lower atmosphere, which has been observed by many coupled modeling systems. And a cold bias then propagates to underestimation of snow ablation and so on. So accurately modeling these snow processes are really important both for the lower atmosphere as well as the snow hydrology. I'll be touching on 4 different model enhancements that we've done in NOAA MP in the recent years. One is accounting for canopy-induced turbulence in the roughness sublayer, and then looking at how that impacts the snow modeling accuracy in NOAA MP. And then focusing on the snow compaction or densification process in NOAA MP. And then enhancement of a new snow albedo scheme that's been integrated with NOAA MP. And finally, a scale-aware enhancement for the snow cover parameterization in the model. So NOAA MP uses the Monin-Obukov similarity theory to calculate the land-atmosphere exchanges. However, the most flux wind profile is known to fail within and above rough surfaces, particularly in the roughness sublayer. So the dashed line here represents the theoretical wind profile from most, but this is known to diverge from observed wind profiles due to canopy-induced turbulence. And this can alter the wind profile within and below the canopy, which can then alter the heat exchanges between the snowpack and the atmosphere, and in turn, ablation and other processes. So we integrated a roughness sublayer parameterization within NOAA MP that updates the most calculations to account for the canopy-induced turbulence. This was based off of Bonin et al., which implemented the scheme into the CLM multi-layer model. We found that by bringing the scheme into NOAA MP, there was a tendency to improve performance across the SNOWTEL stations across the Western US. This is from around 800 stations in the Western US. When accounting for this canopy-induced turbulence with this scheme, we found 64% of sites had reduced root mean square error and 69% of sites had increased correlation. There was an expectation with this scheme that there would be a significant number of sites with actually degraded performance because the scheme was developed with dense vegetation assumptions. And oftentimes in winter, those dense vegetation assumptions are violated. So for instance, deciduous broadleaf forests had significantly degraded performance from this. So it'll be important when bringing this update into any operational instances to account for those vegetation constraints on when to employ the new scheme versus the default Mono-Nabucco similarity theory. Next, I'll discuss our snow compaction enhancement. So NOAA MP simulates snow compaction based off of 3 primary processes: destructive metamorphism, overburden, and melt metamorphism. And we were really interested in updating the snow compaction to be able to more accurately model snow depth, which plays a really important role in the way that NOAA MP simulates the snow cover area. However, most of the snow depth bias in NOAA MP open loop simulations at the SNOWTEL sites was dominated by the snow water volume, or the SWE bias, with an R-squared of 0.83 between the biases. And we were motivated to be able to get the right answer for the right reason and not update the snow compaction scheme to account for the SWE biases. So we ran all of our experiments by constraining the SWE bias through direct insertion simulations that bring in the SNOWTEL SWE at all places and times, and then allow the SWE bias to vary as a function of the uncertainties of other model processes, which we considered compaction to be the largest source of that uncertainty. So we optimized the most sensitive parameter for the compaction scheme across all SNOWTEL sites during accumulation and ablation snow periods, and found that during below freezing instances, there was a robust correlation between the optimal parameter, which is considered static and uniform in the model, with the surface air temperature, with various appropriate lower constraints by elevation or a proxy of the surface air pressure. And so we updated the model in our enhanced scheme to be calculated as a function of surface air temperature with varying lower constraints, and found that allowing this previously static and uniform parameter to vary as a function of meteorological conditions, the snow density in the model was significantly improved, with slight improvements at cold instances, with the black line representing the freezing point. And then particularly larger improvements for the snow density in the model simulations for the above freezing instances, being able to more accurately model the observed high density at these places and times, around having the bias that was in the baseline representation of the snow compaction scheme. There are still some important uncertainties to resolve, and we looked into these as potentially having to do with other model processes, for example, the snow liquid water content. But overall, there was promising results from this scheme, seeing that across the total evaluation period of 2009 through 2018 water years, there were reduced biases at 89% of sites for the snow depth. And then when only focusing on the ablation period for these sites, 99% of sites showed improvement through this model update. So overall, this is indicating that the model enhancement published in James can significantly improve the snow depth in the model simulations, particularly during the key ablation period. And then now I'm going to discuss the snow albedo in NOAA MP. Fanglin in 2019 found that there were overestimates in the albedo in the western US, particularly in the mountainous regions where snowpack plays an important role in the albedo. And part of these uncertainties were due to the semi-empirical representation of albedo in the current NOAA MP implementation, which relies on the BATS or the class schemes. So we brought research led by Su-Shun Lin, integrated the fully physically based NCAR snow albedo model within NOAA MP, and evaluated how that impacted the NOAA MP snow albedo simulations at Rocky Mountain observational stations with spectral observations of albedo not only in broadband, but also visible in near infrared to understand whether we were accurately modeling the broadband albedo for the right reasons. And overall found that the NOAA MP NCAR implementation more accurately matched the in situ observed albedo relative to the NOAA MP default BATS representations, and particularly large improvements for instances of fresh snow with NCAR being able to capture the variability in a fresh snow albedo. And then in the same 2019 paper, Fanglin also reported snow cover biases, in particular snow cover overestimates in the western US. And there's a known scale dependency of both the biases and the snow cover scheme in the model. So we developed a new scale-aware snow cover parameterization using what we considered the most reliable reference snow data we had for the western US. That's ModScag for the snow cover fraction, which is a MODIS-based product, and the SNODAS snow data assimilation product for SWE and snow depth. So what we found was when we used the reference snow data and optimized the snow depletion curve that NOAA MP uses, which relates the snow cover area on the vertical to the snow depth on the horizontal, varying by snow density, was that if we optimized using the same data at 1, 3, 13, or 25 kilometer resolutions, there's various optimal curves depending on spatial resolution, with a slower depletion curve at coarser resolutions and a faster depletion curve at higher resolutions. So this indicates that the model scheme can most skillfully account for these through a scale-dependent parameterization or by tuning the tunable parameters for the depletion curve to vary as a function of the model resolution. So we selected a set of non-dominated solutions for the optimized tunable parameters for the snow depletion scheme and fit a mathematical formula that updates these parameters as a function of the model spatial resolution. And then evaluated whether the scale-dependent formulation improved the snow cover fraction simulations across the western US domain. And in our box model simulations, where snow cover fraction simulations were driven by the SNODAS inputs of snow depth and snow density, we found that there were reduced snow cover fraction biases from the model at 92 to 97% of the pixels, and with evaluations at 1, 3, 13, and 25 kilometers, with these spatial resolutions selected as operationally used resolutions from different systems that use NOAA MP. So the 1 kilometer is the National Water Model spatial resolution, and 3, 13, and 25 kilometers are used by the UFS. And overall, this indicates that if the snowpack or the snow depth and SWE, snow water equivalent, are consistent with the reliable SNODAS product, then we are able to accurately model the snow cover fraction and consistently reduce the overestimation across the western United States with larger improvements at coarser resolutions. We also found this to be the case in our open loop offline NOAA MP simulations in the western US, where the black line is representing ModScag, blue was the baseline NOAA MP formulation, and red is our new enhanced simulations. So the blue baseline simulations had these overestimates across all spatial resolutions with increasing biases at coarser scales, that the enhanced representation of the snow depletion curve parameters removed the systematic bias and the scale dependency of this bias. We started coupled testing with the snow compaction, the snow cover fraction improvements in the WARF NOAA MP coupled system. And we have one test year now that we've begun to analyze for the 2019 water year, representing a relatively wet year for the Western US snowpack. And so in the 2019 water year, the baseline simulation had a systematic cold bias on average of minus 0.9 Celsius across the Western US. And this cold bias was reduced by around 20% by implementing our updated compaction and snow cover fraction parameters, reducing the systematic bias to 0.72, although there's still a significant portion of this cold bias remaining, indicating that other processes in the coupled system are likely playing an important role. I'd like to thank you for your attention and take any questions if there's time. If there's not, please email either myself or the NOAA MP team lead, Fanglin He. Thank you.
Thank you. We have time for a quick question as we switch for a virtual presentation. Yes, go ahead, Christine.
It's great to hear that you have developed the scale of characterization and you work develop course resolution. This scale of characterization is prudent. It's on.
Yeah, thanks for the question. The question is can the scale dependent parameterization for snow cover fraction be applicable to coarser resolutions? And potentially, but we've only tested it up to 36 kilometers, which it was applicable. I wouldn't want to say more than what we've tested, so potentially, but it still needs testing.
All right, thank you. Next, we're going to move on to the ocean, talk about MOM6, and we have Gustavo from NCAR, Marques. So we can see your slides. Everything looks good. So can you hear us? Could you talk?
Yes. Can you hear me?
Yes, we can hear you. Thank you very much. So the floor is yours.
Excellent. Good morning, everybody. I'm Gustavo Marques. I'm going to talk about MOM6 developments towards CSM3, focusing on advancements, challenges, and future directions. This work is being done in collaboration with a lot of people. I'm listing some names here, and I'll list names throughout the slides as well. So the MOM6 collaboration at NCAR started in approximately 2016 when the CSM Ocean Model Working Group decided to replace our older model, POP, Parallel Ocean Program version 2, with MOM6. That's when I came in. And since then, there's been a lot of collaboration with NOAA GFGL, so we have tremendous support from them. There's a governance mechanism that we meet quasi bi-weekly, or what we call developer calls. And it's not just NCAR and GFGL, there's many other institutions, and it keeps growing the number of institutions now using and developing CSM, or rather MOM6. It is an open development concept via GitHub. So anyone is welcome to contribute. And the way we all communicate with each other is via this main repository we call the main branch, which sits into this MOM Ocean fork of MOM6. And then each institution has a fork of MOM6 with a respective branch that we communicate back and forth. And roughly once a month, someone makes up a request into the main branch, and then we all merge and we can use each other's development for our own sciences as well. So this is a very populated table. It's just to highlight how we have been developing MOM6. So we start with the column in the middle, so that's what we have in POP. And our goal from the get-go was to have a version of MOM6 that had all the whistles and bells that we had in POP plus additional capabilities. I'm going to focus on what's in color. So in blue, these are the capabilities that will become default in starting CSM3. So we're moving to a hybrid vertical coordinate system as our default workhorse configuration. We also have vertical structure in the ready coefficient for mixing tracers due to mesoscale eddies. And then we switch into a new solar penetration following Oman 2003. And so on and so forth. I'm not going to go into all the details. Things that we are currently evaluating is in adding wave processes into vertical mixing and backscatter schemes. I'm going to talk a little bit more about them in a few slides, and then enhancing the mixed layer eddies by assuming not a constant of the front length of these mesoscale features. So this is the scheme by Bodmer et al. We've been playing with that to see how that affects the solution. We will not include in CSM3 is the story box model, which was just, has been funded through NOAA. It will start in January 2025. So these are the CSM3 components, and I'm going to briefly go through the resolution. So MOM6 and Psi6 have a nominal resolution of 2/3 of a degree. CAM7 spectral element and CLN5 are at approximately 1 degree, and WAVEWATCH 3 is at 3 degrees. So I'm going to highlight here the components that are relevant to UFS, WAVEWATCH, our mediators, CMAPs, Psi6, and MOM6. And we've been focusing on, mostly on fully coupled pre-industrial control and historical simulation. So the goal of CSM3 workhorse, is a CMIP model class. But we also, in the ocean side, do a lot of forced ocean CI simulations where we do a lot of testing, validating, and tuning. So I'll be talking about both the fully coupled PI control mostly, and then the forced simulations. This is what we have learned over these last few years, but I'm focusing on when we did fully coupled simulations. So our very first fully coupled simulation with MOM6 did not use the spectral element of CAM. We used the finite volume, and we had no problem with lab C freezing. But as soon as we coupled with the spectral element, we start to see the Labrador would freeze in most of the runs. And we can see here in the sea ice concentration for March, the Labrador Sea is fully covered in sea ice. So that was a problem. And we were able to significantly reduce them. So nowadays, the last 20 runs we've done, none of them have frozen. And what seems to be the reason for avoiding this freeze is first use a spun up sea ice and land snow depth initial conditions. So those two things are crucial to avoid having too much fresh water being damped right away into the lab sea. And also reduce the radius where we spread the liquid runoff from rivers. So we reduce from 1,000 kilometers to 250 kilometers. And what that does is, in nature, the freshwater is confined within the coastal currents in the Labrador Sea. And we were spreading over a large radius and putting a lot of freshwater in the middle of the Labrador Sea, which is where convection happens. So we were facilitating this shutoff of convection and buildup of sea ice. So these two things significantly helped reducing that problem. A second problem that we face, and this is very recent as of a few weeks ago, is these plots are showing precipitation in the Eastern Equatorial Pacific. So it's an average between 140 to 90 west. And it's on the plot, you see the month on the y-axis, and latitude going from plus minus 20 degrees in the x-axis. And then again, this is precipitation. And the two plots on the left are observational based. So we see that like in this February, March, and April, you see some precipitation in the southern hemisphere, but no, it's very weak. And now the plots on the right, starting with this 103, 106, those are different fully coupled runs. And we have a lot of precipitation. So this is kind of double ITCZ type of problem in these months, February, March, and April, that is significantly larger than in the Alps. So that was a problem. It leads to a lot of feedback into the atmosphere. It has this feedback ocean atmosphere. So we were trying to solve that as much as we could. And as of a few weeks ago, we've been working on a revised version of the K-profile parameterization for vertical mixing, or KPP. And when we added that component, added the revised KPP, so these are the two runs on the right, 108 and 107, we significantly reduced this problem. So again, fingers crossed, this is now being reduced. It doesn't solve all the problems. This is like compensating biases. It made all other things worse. So we're now working to fix these other things. Now moving to what's good. we have really good Nino 3.4 SST anomalies. So the plots on the right are observational based, and on the left is the CSM, one of the CSM3 PI controls. So it's really good. And so it is a plot from my colleague Rich Neal. So it was significantly better than in the development of CSM2. We also have relatively good Pacific equatorial undercurrent. That was not the case from the beginning. So the top plot, the top left, is the data from the tau moorings at 140 west, at the equator. And then the plot on the right is from our POP simulation. So POP was doing pretty well representing the equatorial undercurrent. Then when we started with MOM6, especially when we started to play with the HiCom1 hybrid vertical grid, the equatorial undercurrent was too weak. And we realized that we were double counting on the background viscosity. So we have this latitudinal dependency, background viscosity and diffusivities. And on top of that, we were adding a constant background diffusivity and viscosity. And that constant one was leading to a Prandtl number of approximately 200, very, very large. So we were killing the undercurrent. And that's why we got these very weak values. When we fixed that, when we set those fixed backgrounds to zero, only relying on this latitudinal dependent one that we have, then we were able to get a stronger undercurrent again. One thing is that there's very little difference between if you use a Z-star coordinate or if you use a hybrid or HiCom1 vertical coordinate in terms of the undercurrent. And overall, it is slightly deeper, the core of the undercurrent than in the Alps. As of a few months ago, the Ocean Model Working Group has decided to use a hybrid vertical coordinate going forward. I've mentioned that a few slides ago. And the rationale for doing so is starting with the pros. So it's the best of all worlds. Like we can use level or Z near the surface where we need high vertical resolution. We can use isopycnal in the interiors, which minimize, in theory, spurious mixing. And in the future, we can start, for example, adding a sigma or terrain falling at the bottom as well to represent bottom processes. So it opens up a lot of possibilities. Again, it's like the best of all worlds. And when we were doing comparison between hybrid and Z stars, like hybrid tends to give better overflows and also stronger AMOC. I've mentioned the appealing of using isopycnal layers in the interior to minimize spurious mixing. So this also mitigates thermocline warm biases. Now the cones is less intuitive to configure. It takes a lot of manual tweak, and we're still learning how to adapt it to the other climates. And that was one of the major concerns when we proposed to go forward with this hybrid. To address these concerns, out of the box with CSM, we have the ability to output in many vertical coordinates in Z, in sigma 0, sigma 2, of course, the native grid as well. And we recognize that this might pose a challenge for modeling some climates, for example, LGM, last glacial maximum. If you use the same target densities that we use in our workhorse for PI control and historical runs, it doesn't work for climates like the LGM. And the Ocean Model Working Group is working with the community to find solutions. Now I'm switching out of our workhorse configuration and talk about some known standard configurations that we've been working on. So first, this is the global eddying permitting quarter degree. So this is not the GFGL quarter degree grid. We built up a new grid from scratch. And we did so we can take advantage of this work that's been done in the Ocean Transport Eddy Energy Climate Process team. So this work here, NCAR, is being led by Hussein Yassin, which is a postdoc at CU Boulder. This is our quarter degree. So we're playing with this idea of reintroducing energy back into the system. So the energy that was lost by mesoscale eddies, we put it back via these backscatter schemes and re-energize the ocean with the hope that will fulfill the need of having mesoscale parameterizations in these quarter degrees or eddy permitting configurations. We also have done eddy resolving. So this is a 1/10 of the degree. This is the same grid that was used with the POP high resolution simulations. And we put that together for a machine learning exercise that was done in 2022. We are now working on a global 112 configuration that will be our eddy resolving configuration within CSM3. We also have done fully coupled simplified configurations, and again, this is open to the community. So there's two configurations. The one on the left is what we call the aqua planet, and the one on the right, it has a ridge in the middle. So those are fully coupled, MOM6, so we're using CAM4 in this case, and CLM and size 5. This was a work led by our grad student, Xiaoning Wu. She's now graduated and has moved to work on the industry, and she has 2 papers on that. And since then, there's an ongoing project, I think is about to finish, that's led by Isla Simpson on infrastructure for easily performing this coupled simplified climate modeling within CSM. You can follow this URL, and there's a lot of information about how to use that here. And then finally, we've been doing regional applications as well. This is an example of a Caribbean Sea and Gulf of Mexico domain that was led by a grad student from CU Boulder that just graduated 2 weeks ago, Giovanni Sejo. And this is the preprint is available here on GMD. And again, since Giovanni has started working with this, we put together a proposal that got funded. It's called Crocodile. It's the CSM regional ocean and carbon configurator with data simulation and embedding. It's led by my colleague Dan Amrine here from NCAR, and we also have participation from Woods Hole. And the goal of this project is to come up with a workflow that will broaden accessibility of regional climate modeling. So we hope that this will be a way of facilitating actionable science applications, for example, in coral fisheries and in marine protected areas. In terms of future developments, I've mentioned the SR box model. So it was recently funded, although the award will start in January 2025, but the team is already starting to talk. So keep your eye open for this capability coming into MOM6 hopefully soon. I mentioned the energy backscatter parameterizations, and also that within the CPT, this eddy energy CPT, but it's not just the energy backscatter that is being that's coming through that pipeline, but also these ideas of putting vertical structure into the mesoscale parameterizations. Work led by my colleague Peter Lauritsen. So this is the heavy lift is in the atmospheric model. We're in CSM, we're moving forward with this idea of reconciling the energy exchange, and by energy I mean the enthalpy exchange. That's the heat associated with the mass exchange. So if it rains, there is the temperature of the rain, and therefore there is the heat associated with that mass that will be accounting for that into the coupled system. And this is a massive work in the atmospheric model. We will start with the atmospheric model and then move to the other components. And again, this is being led by Peter Lauritsen. And we've been working with this idea of automating the generation of the vertical grid, this hybrid grid. So I mentioned that the hybrid grid poses a challenge for modeling different climates. It also, even if you do historical runs, pre-industrial runs, there is room for improvement as you move throughout the seasons and throughout different climate indexes happening, doing El Nino, La Nina. So you can envision having a vertical coordinate that is adapted on the fly that will maximize a quantity that we are working on to improve that representation. So this is a community effort. And then finally, there's this work of simplifying the presentation of surface gravity currents. There's 2 avenues. The first one is led by a postdoc here, Momehel, is the particle in cell for efficient swell or pickles. So this is a simplified wave model that Mome has been working on, and also the uses of theory waves. This is instead of using the WAVEWATCH, which is really expensive for our purposes, and we only need simple information from the WAVEWATCH. There's these 2 other approaches that are being tested in order to replace the wave model in these climate simulations. And that's all I have. Thank you for your time. Happy to take any questions. Can you hear me? Hello?
Sorry, I was muted. Thank you very much. With interest of time, we're running about 5 minutes late. We're going to move on to the next talk. So next we have Cecilia Bitz talking about the sea ice model. Cecilia, are you on?
Yes, I am. So I'm trying to find my window to share. Okay, I think I got it. Is that working?
Not yet.
Sorry?
Not yet.
Not yet. Huh.
Just see you.
Okay, I don't know why. It says share this window. I see. Oh, that's weird. I'll try again.
We see you now.
Okay, great.
If you could maximize slideshow view. Oh, we lost you.
What? You lost it?
We had it and then it went away.
Okay, I'll just go back to PDF instead. Great.
Yep, if you could just full screen.
Yeah, sorry. I'm not very
Don't worry about it.
everything goes wrong when you are trying to work at 6 a.m. Anyway, thank you very much for the invitation to speak today about work that I've been doing for about a decade with a large team here. And I really need to acknowledge them because they've all been essential players in making this happen. And what I'm going to talk about is coupled wave sea ice interactions and some of the consequences for climate and forecasting. So we're really motivated by the fact that there's wind waves that are generated off the sea ice, and these are high frequency and high energy, and they tend to propagate into the sea ice, and that is kind of the historical view that then because sea ice is very heavily attenuating of high frequency waves, what remains is the lower frequency, longer wavelength swell waves, and these can propagate potentially hundreds of kilometers into the ice, fracturing the ice along the way. And we think that as the sea ice has been rapidly declining in the Arctic, there's a lot more area for waves to generate, and the fetch is much larger. And so we'd expect more waves, and then when there are big events like storms that generate higher winds, that would permit the effect of these waves to be even greater, and potentially being a big player in actually sea ice decay during a large storm event like this. And there's some evidence that this is already happening in some of the big ice loss years, with August 16, 2016 as an example. So we also know that our models have underestimated some aspects of sea ice trends in, say, greenhouse gas forced simulations in the Arctic, as well as high frequency variability, which is maybe less well known. And this figure shows that compared to observations, the variability on 3 to 10 day timescales in CMIP models is about 50% too low. And so we think that this could be due to a lack of wave ice interactions. Now, the model requirements to actually start to simulate these effects is to include the impacts of waves on ice fracture, and also to include the impacts of ice on wave attenuation. And among the CMIP-6 models, the models that have started to include some of these pieces are really rare. So we really need to represent waves, flow sizes, and their interactions. And at this time, there was just a few models that had waves, but all ignored the wave ice interactions. And then in the sea ice component, none had a flow size distribution, so that none could represent the dynamic effects of flow sizes, but a few would set the flow size at a fixed value, and the common model size 6 sets it at 300 meters in diameter. But in reality, what we observe is a whole distribution of sizes. And what this kind of old figure, a photograph that was digitized and then showing the edges of the ice flows, shows us is that there's a huge range of flow sizes, many orders of magnitude, and that when we quantify them in terms of their number density, they follow kind of a power law like structure and as a function of flow size, but it's not exactly power law, so we can't just assume it's a power law. And why this really matters is because as flows fracture and become smaller, if the same sea ice concentration is present, but there are more flows, the perimeter of the flows goes way up. And that's the interface with laterally with the ocean. And so if the ocean has heat available, it'll more rapidly melt the sea ice at the edge and increase the sea ice concentration, and then allow more sunlight to be absorbed and amplify the loss mechanism. So there are lots of ways, though, that waves and ice interact. That's just one of them. The waves also transport the sea ice a little bit. They have a stress on the ice. So you can see in this kind of cartoon picture when there's wave fracture occurring, and it allows the flows to converge and shift. And then we also see that this attenuation of the waves very effectively in the sea ice, by the sea ice. It turns out maybe a lesser known idea is that waves also affect the growth. And when there's very little wave present, sea ice grows more like a sheet. So that's known as nihilus. And then when there are waves present, it clumps together as it forms in something known as pancake ice. So we think this affects the sea ice variability on S2S timescale. So that's why I think I'm presenting today and hope you're interested. Certainly affects trends on the climate scale as well. So what we're doing about this is simulating the flow size and thickness distribution combined in the size 6 model sea ice component. What that looks like is an equation of a distribution F. It has transport, and then the flow sizes are influenced by thermodynamics, ridging and rafting, and wave fracture. And those kinds of pictorially are shown here, where the green are all thermodynamic and the blue is wave fracture. And you'll see the ridging and rafting is missing in our model yet. We haven't quite developed that piece of the flow size distribution, but all the rest of these components are active in the model that we develop in, which is size 6. And I'll show you some results. So I just wanted to emphasize, though, among all of these, the only two that really feed back directly on the mass balance are lateral melt and lateral growth, because those involve growth. The others, new ice formations already occurring, and it's just a matter of where do we place it within the flow size distribution that I'm describing here. And then just to be a little bit, complete flow welding is something I haven't mentioned yet, but that's the idea that when there's freezing between flows, it can stick the flows back together, which is a healing mechanism, and grows the flows back up in size. So we've, for a long time in sea ice component models, been simulating the ice thickness distribution, which is just a distribution in thickness alone. So a 1D distribution, we usually call it G. I've heard some people at this conference calling this the categories in the sea ice model, and that's right. We usually have 5 categories of sea ice thickness, and incidentally, this is work I did as a postdoc to develop that in our sea ice component models. But now with the joint flow size and thickness distribution, it's a 2D distribution at every point in space. And the equation is very similar, but it just has a few more terms. It did definitely require some extension to the code. It is an option in size 6, so it won't be turned on by default. You can choose to turn it on, but you'll need to have waves in the sea ice in order for it to really operate, because wave fracture is such a fundamental part of the flow size distribution. And so next I'm going to show you some simulation results. And these are simulations that I'm doing in the developmental version of CESM 3. I'm using the prescribed atmosphere at this time since the model is under development. It seemed like a good precaution to not be using a highly fluctuating version of the atmosphere. But all the other components are, to the extent possible today, the complete components. And I'm using the 2/3 degree tripole grid, which has quite fine resolution for sea ice components, but the ocean and ice model are on the same grid. WAVEWATCH is also present in this model, and it's a coarser resolution, like 2 or 3 degrees. So this kind of features that are unique is that we've turned on the joint flow size distribution in size. We have our own custom wave attenuation scheme, which is now an option in WAVEWATCH. And then something that isn't yet an option in WAVEWATCH, but we have a PR request in, is some modified numerics that improve how waves are attenuated in sea ice numerically. So what this looks like, if we just take a picture from space of the flow sizes in the Greenland Sea, you can see visually they vary very widely. And this little transect of a kind of similar region through our model shows, I hope you can see my mouse, the flow sizes in green where they are reaching the maximum that we permit, which is about 1,000 meters near the coast. And then as we go further out towards the open seas, they're heavily fractured and actually fully fractured to the smallest category at some point. The blue with dots is the sea ice concentration. So sea ice concentration is 0 in the open seas and ramps up in this transition region. And this is where waves, which are about 2 meters high, the significant wave height in the open seas in this day, are heavily damped in the sea ice. And you can basically see the action is all in that region where sea ice is heavily damping the waves, but the waves are also fracturing the sea ice. Now, that's just a transect, but if we look at a more complete picture here, the representative radius, which is the first moment of the flow size distribution in size, has a wide range of their values here for April in the Arctic, but it basically reaches the maximum throughout most of the central Arctic, and all the action is in the marginal ice zone, which is the wave affected part of the sea ice. And because we don't have deformation affecting the flows, it's at the maximum. It's just something we're working on to change, but it actually has a pretty modest effect on feeding back on the climate, because it doesn't really matter whether they're 100 meters or 1,000 meter flows in terms of their effect on the mass balance. But when we're talking about either 2 or 100 meter flows, that has a major effect. In the interest of time, I'll skip this one at the right, but it basically just shows that this day in April, what the various components of processes that affect the flow size distribution look like. And instead, I'll show you some more of the big results, which is that before we added the flow size distribution, the default model had uniform 300 meter flow sizes. And in that case, the perimeter of those flows is very low compared to when we add the flow size distribution. So lateral melt is almost negligible. And we're talking about January here. So this is in winter. We expect there still to be melt at the ice edge. That's normal. And of course, it's not melting throughout the Arctic because it's winter, but the edge is always melting. And when we add the flow size distribution, the fraction of basal to lateral melt has shifted dramatically, about 50-50. And this is true throughout the year with the flow size distribution, as we highly preference lateral melt, and that compared to with the 300 meter fixed size. And that's where we'll be allowing for a higher degree of ice-albedo feedback and sensitivity to forcing. Now, the thickness also changes with the flow size distribution model getting thinner, and it's like a 0.5 meter to 1 meter thinner, and then the overall sea ice concentration is actually reduced. And this is just an example for September. Last few minutes here, want to talk about numerics. And I did mention that the prevailing view is that sea ice damps the the fast high frequency waves, and that's of course true. But what I didn't mention is that there can also be wind generation in the ice, wind wave generation in the ice. And this is a new result that came from observations that really surprised us all. And what we're seeing is that instead of damping these higher frequency wind waves in the ice at 0 to 100 kilometer distance from the ice edge, we're seeing a lot of wind waves still. And even at 100 kilometers, in fact, we're seeing a lot more wind waves than we are swell. So there's wind generation of waves. And when that occurs, we have a situation where we have sources of waves in the presence of the damping at the same point. And in WaveWatch, the way this is treated is with time splitting, but that actually turns out to be pretty inaccurate. And it's not necessary. So if we just merge those two back together again, can talk about this if anyone's interested, the accuracy goes way up and it really makes a difference. It importantly adds more wave amplitude. So we get more wave fracture, higher significant wave heights. So you can see with the improved numerics, all the action right at the ice edge. It's hard to see if you don't have eyes for it, but it's much more significant wave heights in the ice than at the with the older numerics. So with that, I'll end since I'm a little over time and just say, I guess I'm at time. We have successful implementation of the wave ice interactions in size 6 and WaveWatch 3. We've been doing simulations in the 1 degree range. I'm really excited about going to higher resolution to look at kind of the more interesting effects at size and space. But what this code is ready now. We're just adding a few more tweaks to parameters, and we'd like to get additional parameterization for deformation. And like this modification to the numerics is very important. So I'm hopeful that we'll see this adopted in WaveWatch for everyone. I'll end there since I'm at time. But thank you very much.
Thank you very much, Cecilia. Some great work. We're going to move on without questions just for time. You're on time, but we're not on time for the session. Yeah. Thanks for the early morning presentation. So next we have an overview. Yeah, thank you. Overview of the wave model by Jessica Meixner.
Yeah, one last thing, sorry.
All right, good morning, everybody. So as Neil said, I'm going to be giving you an overview of the wave model, WaveWatch 3, in the Unified Forecast System. And first, I would like to take a moment to say thank you and acknowledge my co-authors. So I added a couple late additions. Lucas Jones was Neil Barton and I's Halling Scholar this past summer, and I'm going to show you some work that he did. And then I'd also like to thank the WAVES team, Matt Mazarek, Saeed Bashimi, Ali Salimi, Ricardo Campos, who is our close collaborator at CMUS, and Avitrol, who is our leader. So first of all, I want to talk about, since we're here at the seasonal and subseasonal workshop, what might be a use of actual wave forecasts at the seasonal timescale. So Logan Dawson from OPC talked a lot about this on Wednesday. So one of the big things is safety of life at sea. We also have the shipping industry, who, most of us are probably either wearing something or have technology that was built somewhere else and perhaps shipped to us. So this is a very important aspect that touches our daily lives, even if we are not on that ship out at sea. And then we are all interested in being better stewards of the climate. And so if ships can have better routing and use the force of waves or winds, that can help decrease their environmental impact. We also have things like polar ecotourism, polar ship routing itself. And then we heard a talk earlier this week on wave energy and wind energy, marine resources and fisheries. Waves can have impact on that. And then while the resolutions we're likely going to be using at a seasonal or SFS model are probably too large to really get the fine details of a coastal model. If we downscale that and provide boundary conditions for downscaling, there are many more applications for waves at seasonal scales for that. So again, to talk about the shipping aspect of it and the safety of life at sea, the GEFS V12 model is used to create this product that we see here. So this is an experimental product from OPC that was created in collaboration with CMS at AOML, OPC, and EMC. So this is showing the week 2 prediction of basically this Wednesday to next Wednesday, if we think that there will be a probability of 4-meter significant wave height or higher. And so this also supports probabilistic IDSS. And Logan showed you a very similar figure on Wednesday, along with similar products for winds. So this is extending the use of wave forecasts out to week 2, and then hopefully we can continue that on. So also, waves are at the air-sea interface. So we also want to include potentially waves in our coupled model because of the effects of waves on other components. We just heard a great talk about wave-ice interaction. So we have that. Barry's going to be talking to us next about aerosols. Eventually, we could have wave-aerosol interaction. We have Langmuir circulation, and all of these effects of getting a cohesive coupled model of the whole system. So one of the big things that we used to talk about a decade ago is wave-driven mixing. And so this is a figure from a paper from Belcher et al. And on the bottom, we are comparing SST versus observations. And you'll see that the SST was way too high in the Southern Ocean, and our mixed layer depth was too shallow. And it was found that Langmuir mixing, which is wave-driven, was the missing feature there. And so we can parameterize that feature, but we can also have a sea state dependent mixing for that as well. So taking a step back now that we've talked about kind of why, I wanted to give kind of an overview of how the wave model is coupled into different applications within the UFS as a whole, not just the SFS system. So on the top left, we do have our medium range 2S2S system here, which is our 6-component system, which does include waves. We don't mention it here, but waves are also one-way coupled in the hurricane HAV system. We also have a simplified wave atmosphere coupled model, so we can really look at the impacts between the atmosphere and the wave model. And then also, if we move into the coast, we have the wave storm surge model that is also coupled into the national water model. So going back towards more of the SFS system, I purposefully have a slightly out-of-date image here of our coupled system. We don't have interactions with aerosols yet, so left that out. But I wanted to point out how we are currently in the UFS coupling the wave model. So the wave model is passing the Z0 roughness length back to the atmospheric model. We're getting 10-meter wind speeds back from the atmosphere to the ocean model. We pass Stokes drift for that sea state dependent Langmuir mixing, and we're getting ocean currents back, which is very important. For example, GEFS version 12 does not include currents, but that's a really important feature to capture in the wave model and is, for example, a need of the Ocean Prediction Center. And then you will notice that we only have one arrow here for the ice model. We're just getting in information from the ice. And as Cecilia pointed out, we are not yet feeding that information back to the ice model, but that is something that we could look at in the future. And then one thing that I do want to point out is I did say this was a bit out of date, and it was so that we could really point out what was going on as it pertains to the wave model, but we are actually passing all of this information through the CMEPS mediator. So all of the feedback between the different models are going through CMOPS. So early results. So a big question is, should we include waves? And so to try to start answering that question with some evidence, this summer, Lucas Jones, our Hulling scholar, ran 2 sets of experiments. We were using a 1 degree resolution for all the models. We had a control member plus 10 other ensemble members. We were doing 90-day forecasts. We did this with and without waves. And we had 3 initial condition dates. So November 1st of 1997, 2015, and 2020, all El Nino years. So what did the results look like? So here we've got sea surface temperature. This is the ensemble average difference between waves and no waves. We've got the 1997 November 1st initial condition here in the first column, the middle column, the 2015, and the last column, the 2020 initial condition. And then we took monthly averages for this figure here. So we've got the month 1, month 2, and month 3. And if you can squint hard enough, you probably can't see it, unfortunately. There are some hashes showing where these differences were significant. And basically the takeaway message here is there's some difference, but maybe not that much. And then the question is it a good difference or a bad difference? So we also compared this with Ostia, and certainly for my eyeball norm, we've got wave, this is just for the 2020 initial condition, waves and no waves minus Ostia. And it's really hard to say if one is a huge improvement over the other, either way. We also looked at mixed layer depth. So we do see some changes in the Northern Hemisphere, which is the winter hemisphere, which is where we have more wave activity. So having some differences, some deeper mixed layer depth is expected and probably what we expect. And then the next question, I know we've talked about this a lot this week, is what's the computational cost? So I want to say a caveat here. This was sort of balanced, and it was the 1 degree, and it's about 20 seconds different and an extra 20 processors to include the waves. So not a lot. And so to summarize, waves are at this air-sea interface. We do have uses for wave forecasts at the SFS timescale. We presented some initial results, but this was all at 1 degree. I expect as we increase resolution, we'll see more impacts. We also need to obviously run more dates, more experiments, and this will impact both our science and our computational time. And I believe I am out of time, so I'm going to stop there. And I have a feeling I won't have time for questions, but here's my email if you have any, or come catch me in the hall. And thank you so much.
Do we have a quick question for Jessica? Thank you, Jessica.
All right, next, so the last UFS component that we'll be presenting on, certainly not the least, is the aerosols. We have Barry Baker, so thank you.
Yeah, so I'm going to be talking about the aerosol component. This is a new component within the seasonal to subseasonal forecast system. So you guys may not be totally aware of it, but you're certainly aware of the impacts of aerosols on our climate and weather systems. And so I would just wanted to start, thank everyone that has contributed to this. I know this is a huge team that's contributed, but I wanted to draw attention to the atmospheric composition team. This is a joint project between many of the OER labs here at NOAA, as well as the National Weather Service and NESDIS. And so, thank you for everyone that contributed. And so, just as Jessica did, I would like to show like a little example of how aerosols are coupled. So we talk directly to the atmosphere. We don't go through the CMEPS mediator. And right now we've been experimenting with direct radiative feedback in a lot of our prototypes. And so just to give a little bit more overview of the aerosol component itself, we are using the NASA Go-Kart 2G. This is a joint collaboration between NOAA and NASA to basically use this within the UFS. I believe NCAR also has a project going on to use this within IMPAS. I'll go over the emissions a little bit more on the next slide, but essentially we're including many of the major players in aerosol composition, including sulfates, organic carbon, black carbon, dust, and sea salt. For computational reasons, we turned off the nitrogen component, but overall this has a very low contribution compared to many of the other sources, particularly dust and the biomass burning components, organic carbon and black carbon. And then for all of the experimental prototypes, we use the MERA2 reanalysis as initial conditions for the aerosols. So just to go over, one thing that the aerosol component has to deal with is the human influence. This is a major contributor to the emissions of particulate matter into the atmosphere. And so for the anthropogenic sources, we use the community emissions data system, as well as the HTAP, or the harmonized, can't remember the acronym right off the top of my head, but we use that for the OCBC and sulfate components. And then, there's some other things that we need, for instance, dimethyl sulfide, as well as biogenic emissions. In our current system, we're using a climatology of the biogenic emissions. And then for biomass burning, for the reforecasts, we're using a blend of the QFED and HFED data sets. This is because QFED is based on the MODIS satellite, and that doesn't go back to the time that we need this. So we're borrowing these from NASA, and the HFED is a harmonized data set that goes with the QFED data set. And then for near real time, we'll use the NESDIS GBB EPX fire emissions. And then after 5 days, we assume a persistence for 5 days. And then after that, we blend into a climatology for fire emissions. For dust, we use the FUNCSA dust emission model that's developed at NOAA Air Resources Lab. And for this, there's multiple components. We're trying to drive this more towards an observation-based system. So we're using the BRDF albedo climatology for the drag partition, as well as a newly developed machine learning threshold friction velocity. And so we joined the EP experiments for the GESP 13, starting with EP4A. And so I'm just showing a couple different plots here that showing the bias versus the CAMS reanalysis. So since we started with the MERA2, we didn't want to compare to MERA2. And what we can see is in black, we have the EP4A experiment. So this was the first ones that we joined. And what you can see is that there's basically a large bias that we found. This was mainly due to the dust component and essentially a unit issue in the implementation. And so once we fix that, which is the EP4B experiment, you can see that our root mean squared errors goes down drastically. And one thing that you do notice is that the error doesn't continue to grow in time, meaning that overall the aerosol component at least is really stable, even out to longer forecast leads. And so this is just going in a little bit farther, looking at different dust regions, and you can see that particularly over the Sahara and the outflow region over the North Atlantic, this is where the major biases were coming. So once we fixed the soil moisture parameterization, this was all fixed. And then I wanted to be able to show some comparisons with some in situ observations. So these are AeroNet observations over the Saharan desert. And what you can see is that if we look at the red dots are the AirNet observations themselves. The green lines are the EP4B, where the solid line is the control member and the dashed line is the Ensemble mean. And what we can see is that overall, even at a 3-week, 4-week forecast, we are comparing well to observations in this. And so we're really excited and happy to see that we're stable out to this period. And so what I wanted to do is also show some of our latest results. So this is the EP5R2. And what you can see is that overall, we do fairly well. We are getting some bias, particularly over the Atlantic Ocean and the Indian Oceans. But overall, we're seeing some real good contributions over this. We are seeing some underprediction in the near the poles, but I think that this is a hard region for MODIS to be able to see. This is kind of at the top of its limits for detection. And so I'm a little hesitant about that area, but overall we do fairly well. We do see some underprediction, particularly in the Middle East and the Indian regions, but overall we're doing really well. We did notice that in some particular instances where we have biomass burning in high latitudes, we are starting to see basically some accumulation of aerosols near the poles. We've tracked this down to the wet deposition, the large scale wet deposition in the model. And so we're currently working on a fix for that, and hopefully we'll have some new results very, very soon. But overall, so we've gone in and did this. We can see that with the new wet deposition scheme, we're able to see that a lot of the overprediction, particularly in the polar regions, has been decreased. And so we're really happy to be able to see this. And so on the bottom right is comparisons to high latitude AirNet observations. And you can see that the green line overall is much lower, meaning that the aerosols are being washed out at these high regions, while we're also improving the bias over major biomass burning areas such as Central Africa and the Amazon. And so the last thing that we're really attacking is the dust emission process. So we're going to include this hopefully in a new mini set that we can use to improve the dust emissions, particularly over these major areas. So one thing that we've seen as a bias dating back to the GAS V12 was that we've had an underprediction in Western China, namely the Taklamakan Desert. And overall, so we've developed this new drag partition model that we're going to be trying to write a publication on here very shortly, but it's a new drag partition that was adapted from the Marques 2004 paper, and then we're testing different methods with this on how to actually include this into there. So we have basically 2 experiments, but overall these new drag partitions are showing improvements, particularly over the Sahara, as well as increasing or decreasing our bias over like Western China. We're still seeing a little bit of underprediction over the Middle East, but that might be due to other factors such as soil moisture or wind speeds. We need to look further into that before we can say what it is. But with that, I'll stop there because I know that we're all behind schedule.
Thank you, Patrick. Anybody have a quick question for Barry? Yes.
basically two questions. One is the cost. I asked one question yesterday, but it could be with how much it adds to the carbon model, and the other is
Yeah, so the cost is about 30%. You know, transporting these, in this case, it's 20 tracers. It's expensive. But there are things that we could do in the future to reduce that. You know, for instance, we don't necessarily need 5 bins for dust. I think that we could get away with 2 or 3. Honestly, for the large scale transport, that would probably be enough for that scale. But yeah, it is expensive. There are things that we can do to improve that. And what was there was a second question there. Oh, impact on radiation. So one thing that we've mainly been looking at the bulk statistics, like Northern Hemisphere, Southern Hemisphere. And the good thing is that we're doing basically the same as the climatology, which is what you would expect, right? If your aerosol component was working properly. Is for the bulk statistics, we are seeing improvement. Now for immediate impacts for like severe storms and things like that, we are seeing, for instance, you can see roughly 0.5 degree to 1 degree temperature surface temperature difference. But that's a short-term impact, right?
All right, thank you very much. Our next session is at 10:20, I believe. And we'll be talking about the SFS development plan.
Yeah, so we'll do a quick coffee break, 15 minutes. I'd love to give you more, but we hold off lunch. I think everyone wants to watch 12:30. One announcement, Dr. Cool Shu Shin was here yesterday from GMU. He unfortunately lost his wallet somewhere in the building. We've been looking for it. If anyone sees a wallet at their feet, either here, the conference room, unfortunately doesn't know where he lost it, just keep your eyes out. We really appreciate it.